So we're picking up with the second half of section 1.2 with graphing a piecewise defined function. Now, you've got example 8 there in your textbook that is an example of graphing a piecewise defined. This is not that same problem. This is a different one, just so that you'll have an additional example of how to do that, okay? So what this function says is f of x is equal to x minus 1 if x is less than or equal to 1. It's equal to negative x plus 3 if x is greater than 1. Now, we've worked with piecewise defined functions before, but we only worked with them in terms of evaluating them. For instance, they would say, what's f of 2? And if they said f of 2, that meant we were putting 2 in the place of x. So we came over here. Did we use the top piece or the bottom piece for 2? The bottom piece, right. Because our x value was greater than 1, that would tell me to use this bottom piece, the negative x plus 3. And then we would put 2 in the place of x. So if we put 2 in the place of that x, that would give us negative 2 plus 3. That would give us a positive 1. You can see then that if I tried to do this by plotting points, I would be here for a while. So what is a better way of approaching this is to literally graph both of the functions and then just erase off the pieces that we don't need. So let me show you what I'm talking about. If we have f of x is equal to x minus 1, all right, forget the whole piecewise definition over here. Let's just graph f of x is equal to x minus 1. So you can graph that however you want to. I'm going to make an xy chart over here. So I plugged in 0, 1, and negative 1 and graphed my line. You might prefer to plot your y-intercept and count your rise over run for your slope. Whatever you want to do, x and y-intercept. Graph your line however you prefer to do so. All right, so that's the graph of y is equal to x minus 1. My piecewise defined function said use the graph of x minus 1, but only where x is less than or equal to 1. So I'm going to come over here and say, okay, right here is where x is equal to 1, and the values that are less than 1 would be over here on the left. So that's the only part of that line that I want to keep. I want to keep where it's equal to 1, so close dot right there, and I want to keep where it's less than 1, so I'll keep that left-hand side of the line, and then eventually we're just going to erase off this right-hand piece over here. All right, then graph the second one. For the second one, we had negative x plus 3, so go ahead and graph that there on the same graph, negative x plus 3, however you like to graph lines. Okay, so for negative x plus 3, I had the points 0, 3, there's my y-intercept, had a slope of negative 1, so you could do rise negative 1, run negative 1, or you could have plotted some more points along the way, however you want to graph your line. For this one, we only want the piece where x is greater than 1. So I can come over here and say, okay, right here is where x is equal to 1. I only want where x is greater than 1. So greater than would go this way. I'm going to keep the right half of this line, and I'm going to erase off the left half of that line. I'm also going to use an open dot right there at positive 1, because remember it said x is greater than 1. And so that is what my final graph would look like. For the green line, x minus 1, I only kept the piece where x was less than or equal to 1, so close dot there and less than. And then for the blue line, negative x plus 3, we have an open dot at 1 because it was just greater than 1. We had an open dot at 1, and we kept the values that were greater than. All right, then over on page 94, they talk to us about even and odd functions. Even and odd functions. All right, let's start with even functions. We can define an even function in several different ways. The easiest way to me to recognize an even function is that it is going to be symmetric with respect to the y-axis. Symmetric with respect to the y-axis. All right, what that means is that if I fold my graph on the y-axis, it would literally fold on top of itself. All right, remember when you were little kids in kindergarten and you took a piece of paper and you took paint and you squeezed out the paint out of the tubes and you got these big blobs of paint on your piece of paper, and then you folded your piece of paper in half and you opened it up and it was like magically supposed to become a butterfly or something like that, right? Literally the last time we had this discussion, I went home that night and my son brought me one of those papers. So there it is right there on the wall. Remember doing those when you were a little kid? Absolutely. It basically is blobs of paint, but it ends up looking like a butterfly. Happy thing. When you folded your piece of paper on that folded line is your axis of symmetry. It's what created the mirror image of your paint. So you can think of these graphs the same way. If you had red paint and you came over here with a red paint pen and you drew with a red paint pen this side of the graph, and then you folded your piece of paper on that axis of symmetry, the y-axis, it would transfer that paint over to that other side, right? That's what we're talking about with symmetric with respect to the y-axis. If you took a black paint pen and you put a little blob of paint right there about 2-1, when you folded it over, it would reflect over another little black blob of paint that would graph at -2-1. And so that gives us a way to algebraically define this, that for every xy that you have, 2-1, you're going to have a reflected point -xy, -2-1. All right, let's talk about odd functions. Odd functions are symmetric with respect to the origin. Now, the easiest way that I know to tell you to see symmetry with respect to the origin is it is the exact same graph upside down as it is right side up. So if you'll take your note sheet there on your desk and you'll turn it upside down and look at this graph in comparison with mine that's still right side up here on the screen, you'll notice it's the exact same image, right? So that is symmetry to the origin. I can put my pencil at the origin and spin my paper. It's the exact same image upside down as it is right side up. Now, in order for me to have this point, 2-1, when I turn my piece of paper upside down, in order for that point to be sitting there, there would have to be a -2, -1. So that is my algebraic definition, that if I have an xy, then I'm also going to have a -x, -y when I have an odd function. Now, the last thing that they talked to me about over here is symmetry with respect to the x-axis. If something's symmetric with respect to the x-axis, that just means I draw my graph up here with my red paint pen, and I fold my piece of paper on the x-axis, and that would transfer my paint down here. That would be symmetry with respect to the x-axis. That, however, is not even a function, right? Is that going to pass the vertical line test? No. So it can't be even or odd. It can't be an even function or an odd function if it's not even a function. But while we're talking about symmetry, they do mention that to us. And you'll notice that the point 1, 2 would get reflected down to be the point 1, -2. So for every xy, you would have an x -y with those types of graphs. Okay, so let's go back to even and odd. We want to be able to look at a graph and tell whether it's the graph of an even function or an odd function. But we also need to have an algebraic way of determining whether a function is even or odd. So here's the test that we're going to use for that function. We're going to plug a -x into the function. Now, remember up here we said that for every ordered pair xy, when you plugged in a -x, you would get just a plain y. You would get the exact same y value that you started with. It wouldn't be altered in any way. And that's exactly what we're saying down here, that if you plug a -x into this function, you should get the exact same thing that you started with. It shouldn't be altered in any way. Whereas with an odd function, we said for every xy you would have a negative x negative y. That means that if you plug a negative x into the function, you should get a negative y. You should get the exact opposite of the y value that you started with, and f of x is the same thing as y. So when we plug in a negative x, we should get the opposite of what we started with. So here is our algebraic test. We're going to test functions for even, odd, neither the exact same way every time. We're going to plug a negative x into the function in the place of x. If we get the exact same function that we started with, it's even. If we get the opposite of the exact same function we started with, it's odd. If we don't get either of those things, then it's neither. So determine if something is even, odd, or neither. Plug a negative x into the function in the place of x. If you get the exact same function that you started with, it's even. If you get the opposite of what you started with, it's odd. If you don't get either one of those things, it's neither. All right, so let's look at several examples. Look at example number 9. First off, let's look at it graphically, because we said that was the easier way to determine even, odd, neither. All right? If I'm looking at this graph, what do you think this graph is? Even, odd, or neither? Even. Why even? Yes, symmetric with respect to the y-axis. If I fold this on the y-axis, this side is going to fold right on top of this side. It's symmetric with respect to the y-axis. We could say that it's even. It's not the same picture upside down as it is right side up, right? The way that I'm looking at it right here, it's a V. If I turn it upside down, it's not a V anymore. So definitely an even function, not an odd one. So let's see what that test would look like algebraically. We said plug a negative x into the function in the place of x. So let's come over here and put negative x in the place of x. So that would be the absolute value of a negative x. What happens when you take the absolute value of a negative number? Yeah, the negative goes away. We get the opposite of that. We get a positive. So if you took the absolute value of x or you took the absolute value of a negative x, you would end up with the same kind of outcome. Now, that one's a little not as easy to see as maybe some other ones. So let's look at several more examples. Look at example number 10. All right, for example number 10, let's start with looking at the graphs. Okay, so when we're looking at the graphs, if I'm looking at this guy right here, can I fold this on the y-axis and it fold on top of itself? No, so it can't be even. Can I turn it upside down and it be the same thing upside down as it is right side up? Yes, so what is this? Odd, good. All right, look at the next one. Can I fold this on the y-axis and it fold on itself? Yes, so what is that? Even, good. Look at this one. If I fold this on the y-axis, does it fold on top of itself? No, because I'd have to have like a piece over here and I'd have to have a piece down here, right? How about if I turn it upside down? Is it the same thing upside down as it is right side up? I heard yes and no. Give yourself a point. All right, down here, let's say that this is 0, negative 2. If you turn that upside down, what does that point become? 0, positive 2, right? That is not the same thing upside down as it is right side up. Everything has to be in the exact same places, okay? So it wasn't even, it wasn't odd. That would be an example of a neither, okay? So for our quiz and our test, we should be able to look at a graph and me not give you an equation to go with it at all. Just give you a graph and you look at it and tell me whether it's even, odd, or neither, okay? For your quiz on this material, remember that you're going to have a graphing calculator. So you technically, if I just gave you an equation, you technically could throw that equation into your calculator and look at the graph and be able to tell whether it was even, odd, or neither. But when we get to the test on Friday, after you've had a little more time to process this, when we get to that test, there will be some of these problems that are on the non-calculator page where you have to be able to test them strictly algebraically. You won't have a way to look at a graph associated with them or to throw it in your calculator and get a graph associated with them, okay? So let's make sure that we can do them algebraically only. So we said that if you wanted to find the algebraic test, we would plug a negative x into the function in the place of x. If we got exactly what we started with, it was even. If we got the opposite of what we started with, it was odd. So I'm going to plug a negative x in the place of x in this first function. Negative x in the place of x, negative x in the place of x. All right, what happens if I have a negative cubed? It stays negative, right? So negative x cubed is going to be negative x cubed, and then minus a negative x plus x. So is that the exact same function that I started with? No. All right, it does look like it might be the opposite. Let me strongly encourage you, if you think this is an odd function, take the extra second to factor a negative out of this function, just to make sure. So if I go through and I factor a negative out of this function, if I take a negative 1 out of negative x cubed, I would have x cubed left. If I take a negative 1 out of positive x, I'd be left with a negative x. Then it becomes crystal clear to me, yes, that is the opposite, and that is the exact same function that I started with, so yes, that is odd. And we had already verified on the graph that it was odd as well. All right, look at the next one. For the next one, if I plug negative x in the place of x in that function, that would be negative x squared plus 1. What happens to the negative when you square it? It becomes positive, right? So I have positive x squared plus 1. What is that? Even, because that is the exact same function that I started with, right? I started with x squared plus 1. I ended up with x squared plus 1. That is an even function, and that was the same thing that we had gotten on our graph as well. All right, look at the last one. If I go through and put negative x in the place of x in that function, you told me a moment ago that the negative cubed would remain negative, so we would get negative x cubed minus 1. So what is that? Well, it looks odd, doesn't it? I mean, I had x to the third minus 1, and now I have the opposite of x to the third minus 1, right? Here's why I encouraged you on that very first graph that if you think something is odd, take the extra time to just factor a negative out of it to make absolutely sure. Because this looks odd, but if you factor a negative out of that, it becomes clear that it's not the opposite of the exact same function I started with. Like some of you were saying, if it really is the opposite, every single sign has to change, not just the one out in front. But if I'll factor out that negative, I'll keep myself from making that mistake. So it wasn't exactly what I started with. It wasn't the opposite of what I started with. So this one would be a neither. And that was the same result that we had gotten by looking at the graph as well. Okay? All right. So here is our homework for tonight. I know last night 43 was our challenge. If you did it as the challenge last night, you don't have to redo it. If I check this homework tomorrow, when you brought it up, you could just bring me the 43 off of the previous sheet. You don't have to recopy it. But if you didn't do 43 as your challenge, we went through that one, so I want you to try that one on your own now. Okay?